12.2 talks about auxiliary or characteristic equations with repeated or complex roots. So we start with the repeated roots first. If we're talking about a repeated root in which the auxiliary or the characteristic equation is of the form d minus a squared operating on y equals 0. Then our solution set is e to the 8x, e to the ax, we multiply by x, always, otherwise the same form. Since any multiple of this will do, you can't just have e to the ax, those will be identical. And the general solution is given by y equals some multiple of the first plus some multiple of the second times x. So to start off, we start with a differential equations for the second derivative plus 2 times the first derivative plus y equals 0. So if we let, this is a second order linear differential equation with constant coefficient, let y equal e to the dt be a solution. So y prime is d e to the dt, and y double prime is d squared e to the dt. So this will be 4d squared e to the dt plus 2 d e to the dt plus e to the dt equals 0. If I factor e to the dt out, I'll be looking at 4d squared plus 2d plus 1 equals 0. So that would mean e to the dt can never be 0. It must be that this is 2d plus 1 squared, unless I messed up on it. Let me double check. Yep, I did. That wasn't the intention. I meant to make that 4. So my mistake. The American goes up. That's a 4. That's a 4. There it is. So we know that 2d plus 1 equals 0. So d equals negative 1/2. So our solution set is e to the negative t over 2. I'm so stuck on t. Oh, boy. It's a function of x. E to the negative x over 2, and to really separate those, we multiply that by x. And the general solution would be y equal c1 e to the negative x over 2 plus c sub 2 x e to the negative x over 2. And here's another problem. Same deal. This is a second order linear differential equation with constant coefficients. We let y equal e to the rt or dt. Y prime is d e to the dt. And y double prime is d squared e to the dt. So 4d squared e to the dt plus 12 d e to the dt plus 9 e to the dt equals 0. If I factor e to the dt out, I'll have 4d squared plus 12d plus 9 equaling 0. That would mean e to the dt equals 0. That's not going to happen. This will be 2d plus 3 times 2d plus 3 equals 0. So d equal negative 3/2 is a solution, multiplicity 2. The solution set is e to the negative 3x over, oh my god, I did it again. Again, apologize, I'm so used to t. The applications are in terms of t most of the time. Just old habits are hard to die. I'm sorry about that. e to the negative 3 halves x. Well, to separate between those, you multiply that by x. And the general solution, y equal, this is the homogeneous or particular complementary solution, c1 times e to the negative 3x over 2 plus c sub 2x e to the negative 3x over 2. So as far as repeated roots, that would be it. If you let y equal e to the dx, y prime is d e to the dx, y double prime is d squared e to the dx, y is d cubed e to the dx. So this says d cubed e to the dx equals 0, which is dy, right? So e to the dx cannot equal 0. It must be that d cubed equals 0. So d equals 0. My solution set is e to the 0, e to the 0 times x, and e to the 0 times x squared. So you always multiply by x when you have repeated roots. So it is 1 x and x squared. And my general solution is y equals c1 times 1 plus c2 times x plus c3 times x squared. And there it is. Idea is fairly simple. Now we get, what if I have multiple of those? That's not a problem. So if they give me the equation like that, we say, okay, well, d equal 2 multiplicity 3 and d equal negative 1 multiplicity 3. Oops, that's multiplicity, oh, they're both 3. Okay, I meant to do one of them, that's okay. So that would be what? The solution set would be e to the 2x, e to the 2x times x, e to the 2x times x squared, and e to the negative x, e to the negative x times x, and e to the negative x. So you always multiply by x when you have repeated roots, and the general solution would be y equal c1 e to the 2x plus c sub 2x e to the 2x plus c sub 3 x squared e to the 2x plus c sub 4 e to the negative x plus c sub 5 x e to the negative x plus c sub 6. Of course, the fun part is finding these coefficients. And that's my general solution. So it could go up to any power. Okay, complex roots, that is, if I'm solving a quadratic specifically, the auxiliary or characteristic equation has d equal a plus or minus bj. Most books have a plus or minus bi, where I is the square root of negative 1. Then we know that if d equal a plus bi, we know that e to the bj is the cosine of b plus j sine of b. So e to the a plus or minus bjx, that's ax, bjx. This you leave alone, it's right there. And this gives you a cosine and a sine. So basically, you really ignore that j and you ignore the plus or minus. And you write c1 times e times the cosine of positive bx and c2 times e to the ax times the sine of bx. And I'll show you how that works. So when I look at the problem, let's start with part A. It says solve the differential equations. Again, this is the linear equation with constant coefficients. Let y equal e to the dx. Y prime is d e to the dx, and y double prime is d squared e to the dx. So here we have d squared e to the dx plus 2d e to the dx plus 2e to the dx equals 0. Factor out e to the dx. That will be d squared plus 2d plus 2 equals 0. E to the dx equals 0. That's never going to happen. it must be that d squared plus 2d plus 2 equals 0. That doesn't factor, not a problem. You could use quadratic formula. I prefer completing the square. Take half of the middle number and square it. Square root both sides. So d equal negative 1 plus or minus I. So the solution set is e to the negative t times the cosine of t. Oh my goodness, second part of t. And e to the negative x sine of x. And the general solution is y equals c sub 1 e to the negative x cosine of x plus c sub 2 e to the negative x sine of x. And there it is. And if I move to the next problem, same deal. If I let y equal e to the dx, y prime equal d e to the dx, again, this is a third order differential equation with constant coefficients. In case you're wondering, we don't deal with non-constant coefficients. That's a different class. So we have d, oh, and I need a third derivative. Look at that, almost forgot. So plus 16 d e to the dx equals 0. Factor out e to the dx. You're left with d cubed plus 16d. So e to the dx can never equal 0. It must be that d into d squared plus 16 equals 0. That would mean that d equals 0 or d equal plus or minus 4i. So the solution set e to the 0 cosine of 4x sine of 4x. And of course that's a 1. And the general solution would be y equals c1 times 1 plus c sub 2 times the cosine of 4x plus c sub 3 the sine of 4x. So if this is 0, you're just going to get a sine and a cosine because e to the 0 is 1. And if I want to, okay, and here they already did the work for us. They operated on this, so of course y equaling 0 is trivial. That doesn't mean anything, so that can't be 0. And we have d to the 4th plus 3d cubed plus 3d squared plus 3d equaling 0. Well, that doesn't factor. The possible factors of this, I could take a d out. That would be a d cubed plus 3d squared plus 3d plus 3 equals 0. And again, the possible factors of that would be our plus or minus 1 and 3. Factors of 3 divided by 1. So I try the 1 and see if that, well, 1 is not going to work. Because if I put a 1 in there, that's 3, 6, 9, that's 10. If I put negative 1 and I see if that works, 1, 3, 3, 3, 1, negative 1, 2, negative 2, 1, negative 3, that does work. So I have so far, I have d into d plus 1, and this is d squared plus 2d plus 1, which is d plus 1 squared. So I have d into d plus 1 cubed. So that means d equals 0 or d equal negative 1 multiplicity 3. The solution set e to the 0 is 1, e to the negative x, e to the negative x times x. And if I multiply by another x, there it is. And the general solution, y equal c sub 1 plus c sub 2 e to the negative x plus c sub 3 x e to the negative x plus c sub 4 x e to the negative x, x squared e to the negative x, and that is my general solution. They give me initial conditions. I figure out C1, C2, C3, and that would be it for this section.